All right. So compound interest is why we are interested in exponential functions. So the basic idea is, let's say I have $1,000. We're investing at 5% interest, and let's say it's compounded annually. Then that means in year one, so in year zero, we have $1,000. And then in year one, you get $1,000 plus 5% times $1,000. And 5% of $1,000 is $50. So then you get $1,050. But then in the second year, you have that $1,050, and then you add 5% of the $1,050. And that is $1,102.50. So here's the thing that's happening. Just to do some arithmetic out. So if you have $1,000 plus 5% of $1,000, that's the same as $1,000 plus 0.05 times 1,000. And so $1,000 here is a common factor. So this is 1,000 times 1, and this is 1,000 times 0.05. So the whole thing is 1,000 times the sum of 1 and 0.05, which is $1,000 times 1.05. So another way to think about this is 105% of $1,000. So then it stands to reason that in year two, you get 105% of 1,050, which is going to be 1.05 times 1.05 times 1,000, which is going to be 1,000 times 1.05 squared. And so what happens is you get the function f of x equals 1,000 times 1 plus 0.05 to the x. And my y scale is hilarious here, so I need to change this to like 2,000. There we go. And I'll make a table. And this will be f of x1. Oh, oops, shoot. Sorry, technical difficulties. And so a neat thing that happens here, I'm just going to keep plugging points in. Is it grows a little faster than if you got just 5% of what you started with. So a simple interest means no compounding. And so then that would give you a function sort of like g of x is you'd start with the $1,000, and then you'd get 0.05 times 1,000, but then you just multiply this by the number of years. So instead of getting interest on your previous interest, you'd only get interest on the initial amount, which is called the principal. And so that function, this is of course the same thing as 50. And so if I do 1,000 plus 50x, you can see that the compound interest function slowly but surely diverges away from the simple interest function. So you get a little more interest. All right? So that's compound interest, but that's compounded annually. So the thing about compound interest is sometimes you compound multiple times a year. So, for example, lots of things like car loans or mortgages or whatever compound monthly, which means they compound 12 times a year. So let's say we have $1,000 at 5% compounding monthly. So what happens is your monthly interest rate is your annual rate divided by 12 by the number of times a year you compound. So that's 0.05 over 12. And so then, since there's 12 months in a year, x years equals 12x compounding periods. So your function becomes g of x is 1,000 times 1 plus 0.05 over 12 to the 12x. Because you get a 12th as much interest, but it happens 12 times a year instead of once. And so I'm going to plot that as g of x equals 1,000 x. And just for comparison's sake, I'm going to plug it in here. So a thing that you should notice is that compound interest does not actually grow that much faster when you compound monthly than if you do annually. Like, there's a difference, but it's extremely slight. So one thing is you sometimes talk about doubling times. And so notice that we can actually do it like this. Let's start y equals 2,000. So when do we have twice as much money? But we have twice as much money when y is 2,000. So if I zoom in, you can see that on the monthly graph, it takes a little less than 14 years. And on the annually graph, it takes a little more than 14 years. Not much difference. The general formula here is if we compound n times a year, we get a function f of x equals the principal times 1 plus the rate of interest divided by n to the nt. P is principal, R is interest rate, and n is number of compounding periods. So you can make n whatever you want. So just to, let's delete all this. Let's say x is 1,000 times 1 plus 0.25 divided by n to the x. I'm going to add a slider. But I'm going to zoom out first. All right, so here's this. Let's give us as a baseline the annual interest. So you see that. And so now if I increase n to 10, I get something like that. If I increase it to 100, I get something like that. And as I keep adding zeros, it doesn't get better. It levels off. And it levels off at what's called continuous interest, or continuous compounding. So continuous compounding interest is when n sort of goes to infinity, gets really, 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 really big. And if n gets really, 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 really big, what you end up with is g of x equals p times a number e raised to the RT. And I'll show you that over here. And this should be Rx. You can see that that purple line perfectly matches the green line, or perfectly matches the red line. This number E is usually in your calculators. It's just an arbitrary constant, and it's 2.718281828 and so forth. This is sometimes called the natural exponential base. And it's called that because it sort of just happens naturally when you do sort of processes like this, where you're doing this exponential process, but you're sort of shortening the period in which that exponential process happens. And so it doesn't blow up, it sort of just converges on this very specific number. All right. So, all right, and we're going to talk more about E in the lectures on section 1.6.